lecture on chapter 32, where we're going to discuss the atom and the quantum. How to quantize the atom, in other words. Okay? So we'll talk about how the atom was first discovered to have separate parts, including the atomic nucleus, and then the electron. Then we'll talk about the atomic spectra, which should seem familiar to us because we've already talked about how elements have these light fingerprints, because we discussed that when we talked about the idea of emission, okay, atomic emission. So it's definitely a similar idea. It's just that instead of looking at it from the perspective of light, now we're looking at it from the perspective of understanding the atom, kind of building the atom up both historically and conceptually, okay? So that's going to definitely give us some clues about the structure of the atom. Then we'll get to Bohr's model, which was a key point, the turning point in understanding what the atom is all about, because it is a model of the atom. Then we'll get into quantized energy levels, especially understanding them as waves, all right? Finally get into really what is the modern idea of quantum mechanics, which was, building on ideas that weren't quite right, including the Bohr model, which had some fundamental flaws. And then finally finishing with a simple idea called the correspondence principle. Okay, so going back in history, we want to start first with the discovery of the atomic nucleus. So it was discovered by Rutherford, and what was done in the experiment was a beam of positively charged alpha particles, and an alpha particle is basically helium stripped of its electrons. Of course, Rutherford wouldn't have known that at the time. They just knew that it was a particular type of particle that could be generated, and with a technique, and then basically directed towards, in this case, a thin gold foil. So these two protons and two neutrons, when bombarded on the gold foil, well, they would bounce into the gold foil, right? And nearly all of those alpha particles passed through the foil, kind of showing that the gold almost wasn't made of anything. It had no ability to stop these powerful particles. However, some were deflected from their straight line paths, and a few were widely deflected, and a very small number were even scattered backwards. And so we can see some of the scattered patterns here. So this is telling us that there is a possibility to make collisions. Now, most of the gold is composed of essentially empty space, so the powerful alpha particle passes right through. But there's certain points where there's something that is a major obstruction, a large amount of mass concentrated in a very small region. And if you hit it dead on, then the alpha particle can get bounced backwards. Well, there you have it. You have the idea that atoms are mostly empty space with a very small, very dense atomic nucleus. All right? So these alpha particles must have hit something relatively massive. And of course, relative to the alpha particles themselves, right? And a gold nucleus, we now know, is quite a bit more massive than two protons and two neutrons. Rutherford reasoned that the undeflected particles traveled through empty space in regions of the gold foil. All right? Really just nothing there. While the small number of deflected particles were repelled from extremely dense, positively charged central cores. All right? And each atom, he concluded, must contain one of these cores, which he named the atomic nucleus. All right? And then so that the whole gold was composed of atoms, each of which had its own nucleus. Okay? So that was the discovery of the atomic nucleus. But what else was in an atom? Well, of course, an electron. And let's go to an experiment here to explore the electron. Electrodes in a cathode ray tube under low pressure are connected to a voltage source, causing the gas to glow due to a ray emerging from the negative terminal called the cathode. Slits can make the ray narrow, and the plates could prevent the ray from reaching the positive terminal, the anode. So the idea is we could direct that ray. We could cause it to bend downwards and never make it to the anode. We could actually bend it and affect its path. And this told us that there is a charged particle, and it told us the sign of the charge. So when electric charges were brought near the tube, the ray bent towards the positive charges and away from negative charges. All right, so that definitely tells us that it's a negative charge. Okay, so that in itself is fundamental. Okay, so now we understand that there is a positive charge due to the deflection and relative massive source inside, or location inside of the atom, the nucleus. And now we're realizing there's also a negative charge inside of atoms. But here's the interesting thing. We also can find that by bringing a magnet in, that the negatively charged particles are deflected. Now that is interesting, because the only way for charges to be deflected by a magnet is if they're in motion. So the nucleus wouldn't do this. We don't see bulk movement of the atomic nucleus when a atomic nucleus is presented with a magnetic field, because the charge is at rest. But here we definitely have electrons that are in motion. They're fundamentally moving, and therefore their deflection shows their motion as well as their charge. So Thomson reasoned that the amount of the beam's deflection depended on the mass of the particles and their electric charge. The greater each particle's mass, the greater the inertia and the less the deflection. The greater each particle's charge, the greater the force and the greater the deflection. The greater the speed, the less the deflection. And that's, so if you recall the idea of electromagnetic induction and the relationship between moving charges and magnetic fields and forces, these are all the ideas that Thomson was using in these early discovery experiments of the electron. And by piecing together these different quantities and finding the formulas that then could be tested with the right experiments, the fundamental charge of the electron was discovered. The charge of the electron, E, was discovered. All right? Furthermore, Millikan came up with an experiment to independently determine the amount of charge in the fundamental quantity, the charge of an electron. And that was done by spraying tiny oil droplets into a chamber between electrically charged plates in a permanent electric field, no magnetic field in this case. He adjusted the field so the droplets hovered motionless, and when the downward force of gravity was balanced by the upward electric force. He found that the charge on each drop was always the multiple of a single value. So it went in steps, it was integer multiple steps, and that was the fundamental charge of the electron. So between these two experiments, Thomson's experiments with cathode ray tubes and Millikan's experiments with levitated tiny oil droplets, we were able to determine both the mass of the electron and the fundamental charge of the electron. Okay, so this was really laying the groundwork for our modern understanding of the atom. Now we understood that it was composed of nuclei with positive charges. It had electrons maybe outside of the nucleus that were much smaller and obviously not able to deflect an alpha particle. And that started to give us an idea, a structure. It allowed us to ask more questions. How does the electron and the electrons around the nucleus, how are they structured? How are they oriented? What interaction is there between the nucleus and the electrons? And to start understanding these questions, we started to experiment with light and its interaction with transmission and absorption in atoms. And a very important experiment was the lines that were discovered by Balmer that corresponded to the simplest element there is, hydrogen. So the hydrogen spectrum starts with a line in the red region, followed by one in the blue region, and then several lines in the violet, and eventually many in the ultraviolet that are invisible to the human eye, but certainly visible to certain detection techniques. So spacing between these lines became smaller and smaller from the first red one, so this would be the large spacing, onwards to the subsequently smaller spacings. Okay? And the spacing became so close that they were essentially merging. By the way, this would be approaching, in our modern understanding, ionization. That would be the electron actually being liberated from the attraction of the atomic nucleus. So Balmer first expressed the wavelengths of these lines in a single mathematical formula, but he was unable to provide a reason why. Right? It worked. It represented the data, but why does this convenient formula of integers? Why is it working? Because it seems kind of ludicrous that this is really the behavior of electrons with a atomic nucleus. Well, Rydberg noticed that the frequency of the lines in certain series and other elements followed a formula that the sum of the frequencies of the two lines in such series often equals the frequency of a third line. This relationship was later advanced as a general principle by Ritz, and it's called the Ritz combination principle. All right? And here it is. Here's the idea, is you can have transition energies, and since what's actually happening is you're going from a third energy state to a second energy state, or from a third energy state to a first energy state, or from a second energy state to a first energy state, that of course the sum of going from 3 to 1, or rather going from 3 to 1, is the sum of going from 3 to 2 plus going from 2 to 1. Right? As we can clearly see, the sum of the lengths of the red arrow A and the green arrow B equals the longer blue arrow C. All right? So Bohr reasoned that the electrons occupy stationary states of fixed energy, not fixed position, at different distances from the nucleus. These are the so-called Bohr orbits. Okay? And by looking at these orbits, it made sense with those energy levels. It made sense with the way that photons interacted. We were able to be absorbed by an atom and then re-emitted. And it certainly explained the Ritz combination principle, because we can clearly see A plus B equals C. All right, electrons can make quantum jumps. Quantum because it's quantized. There's no way to say jump halfway between n n equals 3 and n equals 2. It just doesn't exist. It's impossible to end up halfway in between. Light is emitted when such a quantum jump occurs from a higher to lower frequency. Thus, the energy is equal to Planck's constant times the frequency of the light. So then we would say that the energy differences would always be these integer multiples of hf. Okay? So that was the idea. That was taking the idea of discrete bits of energy, which had originally been proposed by Planck to understand blackbody radiation and light, but now applying it to the atom based on the structural understanding that atoms have electrons and a nucleus, and that there's some interaction, and maybe the nucleus is like the sun, and maybe the electrons are like planets, and maybe they're in orbits, but the orbits are quantized and they're stationary. And so this was an interesting turning point in science, and Bohr got, rightfully so, a Nobel Prize for this, because it was so revolutionary, and it really was so important for understanding what the atom is, but also it had some serious flaws to it, because how could an atom be stationary if it's in an orbit? And how can an orbit be quantized? Because it's kind of like having it both ways. You can't treat electrons like planets, but then also not treat them like planets, because certainly planets aren't quantized in orbits. You can have any stable orbit at any distance from the sun. And furthermore, if a planet was in orbit around the sun, then that planet would be accelerating. A planet is accelerating. It has a centripetal acceleration. Well, if an electron is accelerating, an electron emits light. That's right there, one of the fundamental principles of electromagnetism. That's how all electromagnetic waves are generated. Any accelerating electric charge produces a changing magnetic field, which thus induces a changing electric field, creating the self-propagating wave we know as light, an EM wave. Well, here's the thing. If that's the case, if an accelerating electron in a stationary orbit, such as n equals 3, around an atomic nucleus, is really doing that, if it's really accelerating, then it would have to produce light, and it would have to lose energy, and it would in the process of emitting energy, it would spiral inwards incredibly rapidly. There's no way to fit the numbers and say, oh well, electrons are spiraling inwards, but it takes millions of years. No, it would happen in fractions of a second, which means every atom would be fundamentally unstable, and that's clearly not the case. So how do you reconcile that these orbits are quasi-orbits that are quantized, and indeed the electron must be in motion, but at the same time it's not radiating away energy? How do you deal with that? Well, here comes Louis de Broglie, and what he hypothesized was that it was the wave nature of the electrons that was allowing this all to happen. And the issue of thinking of the acceleration of the charge was that we were thinking of it as a particle, not as a wave. And at this point, the idea of electron diffraction had already been shown experimentally. We're talking early 20th century. So we already understood that electrons were waves. So perhaps the quote-unquote orbiting electron around the atomic nucleus was behaving more like a wave than a particle. And thus, it wasn't actually orbiting, it was instead resonating like a fundamental frequency on a string, or any harmonic on a string. All right? So de Broglie showed that a Bohr orbit exists where an electron wave closes in on itself constructively. It's a standing wave. The electron wave becomes that standing wave, like a wave on a musical string. And indeed, we can draw the electron matter waves as if they are waves on a string, where they have to come to a point where there's an integer multiple of full wavelengths. Notice, right, this would be a full wavelength from here to here. That would be 1 lambda. And then we'd have an integer multiple of lambdas to fit on the entire circumference of the circle. Okay? So in this case, we would have 1 lambda, 2 lambda, 3 lambda, 4, and 5. So this would be the fifth energy state, because this would be the fifth longest wave. So it would be 5 times shorter than the longest possible wave that could fit on this circumference, and it's a standing wave. So it's taking it's just a circular standing wave, which would be impractical to do with a string, right? But it works on this quantum mechanical level, on this idea of matter waves. Okay? So an orbiting electron forms that standing wave only when the circumference of its orbit is equal to a whole number. Right? Only when it's equal to a whole number of multiples of the wavelength. And of course, lambda is the expression we use for wavelength. the Greek letter. So when the wave does not close in on itself, like in this case, that's a forbidden orbit. That's why there's no intermediate step. That's why you can't go from n equals 3 to n equals 2.5, because you can't have destructive interference. You can't have an unstable wave. So the circumference of the innermost orbit, according to this picture, is equal to 1 wavelength. And then you go from integer steps from there. And now you see how it all makes sense. Why then you get the Ritz combination principle. Why you get these energy levels that get closer and closer together. Because as you start adding more and more wavelengths, the circumference isn't that much bigger. Okay, so it all starts making sense. Okay, so here we can imagine them on strips of paper that were kind of circling around. Nice visual representation of the idea of standing electron matter waves as our understanding of quantized energy states inside the atom. All right, so this model is much better than the Bohr model because it explains why electrons don't spiral closer and closer to the nucleus, causing atoms to shrink, because they're not actually in motion. They're just in a standing wave property. If each electron orbited is described by a standing wave, the circumference of the smallest orbit can be no smaller than 1 wavelength, right? As we said. As long as an electron carries the momentum necessary for wave behavior, atoms don't shrink in on themselves, okay? All right, so this then leads us to, at this point, we're probably in the 1920s historically, right? Kind of moving from the late 1900s up to the 20th century, up to the 1920s. And we get to what really is modern quantum mechanics. And we can really say that modern quantum mechanics starts with Schrödinger, okay, made famous by Schrödinger's cat, if you've heard of it. But here we have Schrödinger's equation rather than his cat. And this is certainly an equation that's beyond the scope of this class. It's a second order partial differential equation, which is a thing in differential equations. But also it's an amazing equation because it actually represents the three-dimensional behavior of the waves. It tells us the probability of the electrons being in certain locations. It tells us where they can be. It tells us conservation of energy and momentum, angular momentum. And the amazing part of this equation is that it is an equation that tells us about the electrons in a definitive way. It's a definitive governing equation. And it also tells us that the electrons, by having a wave-like property, must have an associated uncertainty. We saw that when we explained the very duality of light, that light has to have a fundamental uncertainty to it, because only then can single photons, be randomly end up in different locations but follow the overall property of a diffraction pattern. Well, that was Heisenberg's uncertainty principle. Well, if we're applying a wave-like nature to electrons, but also acknowledging that they have a duality and are particles as well, then they must have a fundamental uncertainty, and indeed they do. And thus, this equation is a probabilistic equation. It tells us not where electrons are located, but the probability of them being located in certain places. All right? So in quantum mechanics, in Schrödinger's wave equation, the thing that waves is the non-material matter wave amplitude, a mathematical entity called the wave function. It is represented by the symbol psi, spelled psi, and all the information about the matter wave is contained in that wave function. Okay, so it's quite a derivation. It's a whole subject in itself. A couple semesters of upper division physics to really understand something like this. But the idea is that it's a probabilistic. It's not telling us where the electron is, but where it might be, where it's most likely to be. All right? So the progression from the Bohr model of the atom to the modified model with the de Broglie waves, which was a major breakthrough, all the way up to the Schrödinger model, will look a little something like this. Starting off with treating them like orbits, like a planet, but then realizing that doesn't work. Moving on and saying, okay, well, as long as we think of them as standing waves, then we're in better shape. But the thing about the standing waves is it doesn't take into account the fundamental probabilistic nature of the electrons. So then we get to Schrödinger's equation. And we understand that the electrons are actually in probability clouds. They're never truly located in one place. They're not actually a wave. They're not actually a particle. They're a probabilistic entity, right? That's when we say that what waves is the matter wave amplitude, the actual likelihood of it being in one place. So as to why electrons orbit in only certain orbits, a compelling explanation views orbital electrons as what? Okay? This is kind of going back to the previous material. Make sure it's sunk in. Make sure you can answer this. Otherwise, maybe it's not sinking in fully. But of course the answer is standing waves. All right, so finally the correspondence principle. So the correspondence principle says that in a new theory, for it to be valid, it must account for the verified results of the old theory. Okay, so this is a really important idea. This will apply again when we talk about Einstein's special theory of relativity and even his general theory of relativity, although it's easier to show with the special theory of relativity. Because that one it has correspondence with Newton's laws of motion. And likewise, quantum mechanics, fundamental new physics, must work at the macroscopic scale. It must not invalidate everything we know, such as conservation of energy, conservation of angular momentum, Newton's laws of motion, right? And indeed it doesn't, because it just shows that the probabilistic effects, the wave nature of matter, is so minuscule, so impossible to measure that it doesn't show up at the macroscopic scale. That's correspondence, all right? So to which of these does the correspondence principle apply? Schrodinger's equation leads to Newton's equations for orbital motion of satellites. The energy of a particle can be expressed as E equals mc squared. Diffraction can be explained with either particles or photons. Well, of course, the answer is all of the above. Unlike Heisenberg's uncertainty principle, the correspondence principle is a general rule. Old and new theories, they must overlap. And there are, of course, some systems that are kind of in the middle where you might have to pay kind of attention to the quantum behavior, but not much, right? Maybe it only creates a 0.01% error in your measurements, but maybe you care about that 0.01% error. So it's so interesting to think about when is it important, when is it not important. All right, so that concludes our first introduction to the atom, and we're going to get more into the atom into the next couple chapters. Specifically, we're going to zoom in on the nucleus, because you may have noticed in this chapter we overlapped with a lot of material in terms of understanding photons and Heisenberg's uncertainty and so on, and energy levels. But we're really going to do something new in the next couple chapters. We're going to talk specifically about those protons and neutrons, collectively known as nucleons, right down in the tiny atomic nucleus at the center of every atom. And I think it should be very fascinating. All right, well, thank you so much for watching this video on our introduction to the atom. I hope it has been interesting and informative.